Hello everyone. In this video we're going to be learning one of the last couple of ideas we need to talk about in the course, and this is the idea of table doubling. It's going to be used to solve a particular problem that shows up all the time in data structures and algorithms and even designing programming languages. So here's our problem. Suppose we have an array of size 10. And you allocated this array dynamically, and maybe you want to insert something new into this array, and you have no additional space. So suppose we have an array of size 10, and now we want to insert an 11th element into the array. This is a very common thing that could happen. We've actually seen that this could become a problem several times in this class. In particular, when we worked with heaps, one of our implementations for a heap was to store them as an array, and it was possible that we'd eventually need to increase the size of the array that represented the heap. And in doing so, we would need to allocate more memory to insert those new elements. So that's one place we've seen this before. We've also vaguely come across this when we looked at open address hashing, when we had to deal with the issue of running out of space in our hash table. So we've seen this problem before. So how are we going to deal with this? One way to deal with it might be to just reallocate some more memory. So let's say we reallocate an array of size 11. And then after we reallocate that array, we insert the 11th thing. So then we insert the 11th element. And then we keep going through our application, then eventually, oh dang, we need to then reallocate an array of size 12 so that we can insert a 12th element. So then suppose eventually we need to insert a 12th element, so we need to reallocate an array of size 12, and then insert the 12th element. And then we keep going in the application, and suppose we need to do it once more. We reallocate an array of size 13, and then insert the 13th element. And let's say we keep doing this for a while. Our question is going to be, let's suppose we needed to make the array, we kept doing this until the array became size 100. How long here meaning in terms of complexity, would it take to insert elements and make the array size? I'm going to write 100 here, but in our heads we're keeping in mind that that might be some variable. Let's say we had to insert n elements into the array. So let's think about how long do the operations we talked about take. If we scroll up, to reallocate the array of size 11, what we need to do is we need to, one, reserve the memory for that array, and then copy all of the old array into this new memory address. So if we're going to think of a runtime for this reallocate array of size 11, that's going to be 11 times the constant time it takes to run that code. And then the insertion actually only takes constant time. And then the next one, it would be a 12C and a 13C for the allocations, and a C and a C for the insertion operations. So if we're trying to compute the total runtime, how many copies of C would we get, and how many copies of this 11C, 12C, and 13C, and so on would we get? So if we do this, we'd get maybe 90. So T of n would equal maybe 90C. This first term coming from the inserts plus all of the other operations, which would be I need to resize it to size 11, and size 12, and size 13, and I would do that up until I eventually resize it to be size 100. And this comes from the reallocation cost. Let's try and determine about what this is equal to. If we notice, that's a nice easy summation, 11C plus 12C plus 13C up to 100C, and ignoring some of the details, this term over here would cost about 100 times 101 over 2 times C. It's an arithmetic series, and we're going from 10 to 100, so maybe we need to fudge that by a little bit, but it costs about 100 times 101 over 2. And if we look, that's definitely going to be the dominant term in this expression. And as we might have guessed, there's nothing special about the number 100, so if we're thinking about the cost here, maybe we would say it's T of n is in, that would be like n squared over 2, so this would actually be in theta of n squared. If you want, you can go through and derive that yourself, but it's sufficient for us to just say that seems like a reasonable guess. Why was this such a bad problem, though? So what's the issue here? One, can we do it more efficiently? And if so, what is causing the inefficiency? The inefficiency is that we were being very judicious with our memory reservations. Every time we'd insert a new element, we only increase the size by 1. But maybe we expect that for some reason we're going to make several insertions after the fact. So how might we deal with that? The name of this topic might actually give it away, which is we're actually going to double the size of the array when we need to make that insertion. So our solution to this problem is, first, let's address the problem. Can we do this more efficiently? The answer is, of course we could. We could when we needed to reserve more memory, reserve the entirety of the RAM for the computer. However, that's not very good for the spatial complexity of the problem. We might have this concern that we don't want to reserve too much memory, we just want to reserve enough that we don't need to make too many additional reallocation steps. So to hedge our bets between the memory and the runtime, what we're going to do is double the size of the array. So our solution, oops, this is too big of a pen. So solution. We're going to start with an array of size 2, and when we must increase the size or reallocate memory, we double the capacity. What do we mean by capacity? This is a common term used for this. We will have some amount of space reserved for the array, but not all of that is currently occupied by relevant parts of memory. So we might have an array that has data in one part and then free space, free real estate over here. The total size of this array would be the capacity of the array. So this is our array A. And then there's some part of this array that corresponds to the actual data we care about, and some part of the array that corresponds to memory we have access to but haven't yet to put anything in. This is the idea behind table doubling. We want to determine if this has a more efficient implementation, but for now, we'll settle with the idea, which is whenever we need to reallocate memory, we're always going to double the size of the array. This is tangentially related to a sort of kind of comical statistical problem, which is brought about in World War I, when they were capturing German tanks. The American government was during the war, and the tanks were numbered based on when they were produced. So they captured, let's say, tanks 12, 48, and 62. They then needed to, given those tanks, determine approximately how many tanks did the Germans have in production. This was a useful problem for a military application there outside of the sort of data structure application. And you could do some analysis about what you might expect to happen out of these sort of things. So this is related to some more interesting, purely statistical problems that you can read about. That's called the German tank problem if you want to read deeper into some of the probability that might be underlying this. Or you can look up this is called table doubling. You can look up some of the theory behind it. For us, we're going to analyze the runtime of this and just take for granted that it's a good idea to do it this way. But that will be in our next video.